We were just looking at this example here of an example of some, to illustrate that x, some vector of random variables respecting a particular graph does not imply that any of the variables are conditionally dependent. And so we had x1 and x2 and x3 independent for our little example here, and of course the distribution factors. And so we observed that respected this graph G, where we had 3 vertices and none of them were connected. And we were looking at this other graph here, where we connected x1 to x2, or 1 to 2. Let's call that, I don't know, G prime. And I claimed that x also respected this. And the reason why is because, try to squeeze both of these formulas on the same page. The reason why is because, well, if we wrote, so we wanted this factorization to look like this thing. So that, of course, because that's the definition. And we have x1 has no parents, so we're all set there. x3 has no parents in the graph, so we're all set there. And x2 has x1 as a parent. So we would need this factor, probability of x2, to be equal to this in order to match up with the definition here. And we observed that it does, because that's just what conditional independence means. And so it also respects this. And then you might say, well, wait a second. I mean, so the thing that might be confusing to you would be if you came across a graph in the wild and somebody said, gave you this graph and said that the x respected this graph, then you might look at this and say, oh, well, x2 depends on x1. That's what this sort of looks like. That's what it looks like this is saying. But that is not what this is saying. It is not saying that x2 necessarily depends on x1. What this is saying is that the distribution of x factors in a way that can be represented by this graph. So it factors in a way that respects this graph in this sense. Okay, so I hope that was clear. Maybe I'll give you one. Let me give you one other example for this same thing. We could connect all of these, right? If we connected all of these, let's say 1 to 2, 2 to 3, I'll just put them in any arbitrary order, and 1 to 3, you could switch out the arrows as long as it's still a DAG. And x would also respect this, in this case, where they're all independent. G double prime. And it's just for the same reason. Because you always get these sort of, the conditional independence properties give you that these factors can look like these factors up here. Because you can drop the dependence on the parents. Okay, so I wanted to just illustrate. So something this also illustrates, this little example is the following. We'll need a little definition. We will need a definition or terminology. A complete directed graph. I won't write this whole thing out formally, but a complete directed graph is a graph in which all of the vertices are connected to all of the other vertices. So for example, the one I drew, so this is a complete directed graph. The one I drew earlier, I guess I erased some of the edges, but if we added these edges back in, this would be a complete directed graph. It's a complete graph that's directed. Complete graph has vertices, has edges between all the pairs of vertices. So it's just a directed graph that's complete. And continuing along this line, the lines of this remark, a little more general example, similar to this yellow one here. I'll put it in maybe yellow. any distribution on n variables respects any complete directed acyclic graph. So that's a little exercise that you might want to take if this isn't all very clear to you, then that would be a good exercise to do to check that. So this was one example of that. X respected the complete directed graph G double prime. Continuing with a couple other remarks here about this definition. So we had this, remember the definition here, we had that here we had x was this vector of random variables x1 through xn, and I didn't really say anything about are these one-dimensional, or maybe each of these could be vectors. And so, of course you could always combine. Maybe we had x1 through xn, and maybe they all started out as one-dimensional, maybe real valued or something like that. And then we combined x1 and x2 into a new, or maybe we combined xn and xn minus 1 to make a new random vector. Then we could just, we could apply the same definition using xn minus 1 as a vector instead of just a real valued thing. So let me just write it down here. We can combine random variables into vectors and just use, and the same definition applies. So for example, if we had some graph on x, y, and z, something like this maybe, we could always have x1 be a vector, y1 be a vector, and z, etc. You get the idea. And the same definition would apply. We would say that the vector, in this case it would be x, y, and z, respects G, or their joint distribution respects G, if the joint factors in this way. And here, xi, of course, will be a vector-valued quantity. So it would be like probability of x given whatever its parents were. I forget, let's see. Well, x has no parents, so this would be the probability of the vector x times the probability of the vector y given x times the probability of the vector z given x. So you can always lump them together into vectors. And one more remark here, which is maybe it's not really completely obvious, is that if you have, so here we wrote down this formula, and we knew that this was, of course, according to the definition, we said that this joint distribution was equal to this right-hand side. But what if we just started out with a bunch of conditional probability distributions over here, and we multiplied them, if we started out with some graph, like up here, like this one, what if we started out with some graph and we wrote down this expression, and what if we just defined some probability distributions, a distribution on x1, a distribution on x2 for each x1, a distribution on x3 for each x1, and so on, and we multiplied these all together? Would that define a proper probability distribution on x1 through x6? Would it define a proper joint distribution, proper in the sense that it integrates to 1? Maybe not, it's maybe not immediately, maybe not immediate that is the case. And it turns out, though, that is true. So let me just write that. If the factors are normalized conditional distributions, then the product is normalized also. The product is going to be the joint distribution. And it's not too hard to prove that. That's actually maybe a good little exercise to do also. That's actually, yeah, I would highly recommend that actually. It's not hard to prove, and it's very instructive for getting some intuition. It's very instructive actually for getting some intuition into the inference. So why these graphs are useful for doing inference or for visualizing inference algorithms. So yeah, this is a very good exercise, come to think of it. Exercise. So you should definitely prove that to yourself. And I want to emphasize one more time, we're talking about all this, all this stuff, all this conditional independence and conditional dependence stuff. And I want to emphasize one more time that the reason why this is so important is for tractable inference. So recall, to keep in the back of your mind, the reason why we're going through all this and why we're so concerned with conditional independence is that it allows us to efficiently, if we can get some good conditional independence properties, we can efficiently, tractable or efficient, well, tractable meaning, I guess, at least that it's possible, and hopefully not too inefficient, inference. So this is, always keep that in the back of your mind here. This is the fundamental reason why we're so interested in this conditional independence properties, these factorization properties of the distributions.